not be able to reply to you.
That is fine. Simply continue. I mean, rejoin later. Okay.
Yeah.
So yesterday or in our previous class, what we did multiple integral or double integral. So we talked about, I mean, evaluating. We talked about evaluating this integral over the region D, where D was a general region. D was a general region. Okay. Now, so far, what are the problems that we have considered, and where we were trying to define the domain D, what we did it in Cartesian coordinate system. Okay, but you will see that in many problems, I mean, the domain D may not be easily recognizable if you want to express it in terms of Cartesian coordinates. Okay, say for example, suppose I have a domain something like this. I have a domain something like this. Although it is recognizable, say suppose this is the circle x squared plus y squared equal to 1. Okay, so now you know that again, if I want to express it in terms of I mean Cartesian coordinates, then what I'm going to have, like here again, it is going to be bounded by the graphs. I mean 1 minus x squared. It is going to be something like this, isn't it? It is going to be something like this. Fine.
Yes.
And again, I mean, if you're the function that is given to you, I'm talking about this integrand, right? So depending upon this integrand, I mean, your computation is going to be your simpler or I mean complicated. And again, you know that you have to work with, I mean, some upper and lower limit like this. That may be cumbersome. Or you may have something like this. You may have something like this. Say, suppose you have this shaded portion as your domain, shaded portion as your domain. So in those cases, you can easily recognize that using polar coordinates may be the better option. So that is what we are going to do. We are going to find out, I mean, double integral over domains which are expressible in terms of polar coordinates. Okay, and you know that I mean Cartesian and polar coordinates. Say suppose this is x, this is y, and we are thinking about a point xy in such a way that if you I mean join the origin to the point, it makes an angle theta with x-axis, and the length of this vector OP, it is r. So then you know that simple transformation x equal to r cos theta, y equal to r sin theta, and obviously your r square equal to x square plus y square gives you the relationship between the polar coordinates, your r theta, and the Cartesian coordinates x, y. Okay, so now what we are going to do, we will try to find out double integral over polar region. So basically, polar region means regions that are expressible in terms of polar coordinates. So the polar coordinates. Okay. So for this, what we are going to do, see, as before, I mean in Cartesian coordinate system, we started with a rectangular domain. Okay. So here also what we are going to do, we are going to start with a polar rectangular region. So what is a polar rectangular region? Polar rectangular region is such that, I mean, if you can express the domain in terms of something like this. Say, suppose it is in polar coordinates, and if R lies between, say, maybe I can call it A and B, and similarly, theta lies between, say, alpha and beta. So these type of region are called polar rectangular region. Okay, so it is going to be something like this. It is going to be something like this. Say, suppose I have. Okay, it doesn't do like this. Okay, suppose this length is A, and suppose this whole length, this is B, this is B, this angle is alpha, and this whole length angle, this is beta, right? So then this region, then this bluish shaded region, it is nothing but the domain D. It is nothing but the domain D. Okay. So now, as before, what we are going to do, we are going to divide this polar rectangle into some sub-rectangles. So what we are going to do, I mean, for this range of R, so this interval, I am going to divide it into sub-intervals. I am going to divide it into sub-intervals, like say R not equal to A, then R1, R2, etc. And then finally, your say Rn equal to B. And similarly, what we are going to do, like again, subdivide this interval into something like say theta naught equal to say alpha, then theta 1, theta 2, etc. up to theta m, say this is equal to beta, and so on. So then this is going to look like, and again, those intervals doesn't have to be necessarily, I mean, equally spaced, Okay. Now, suppose I consider a sub-rectangles out of all those rectangles there. So in such a way that this sub-rectangle, it's I'm going to call it say Rij, and it is defined by your R theta, such that your R lies between I minus 1 Ri, and theta lies between theta j minus 1 theta j. Is it okay? Fine. So this is my I mean sub-rectangle Rij. Okay. And then what we do, I'm going to consider. Of course, this is 0, and you can still consider it to be xy. And then what we are going to do, we are going to take a point here. That point here, say Ri star and theta j star here, and you may consider those points to be like say Ri star. It is simply given by half. I mean Ri minus 1 plus Ri, and theta j. Theta j. Okay. So now next step, what we are going to do. As before, I mean, when we were defining double integral, it was nothing but sum of all the integrals over those, I mean, sub-rectangles, isn't it? All integrals over those sub-rectangles. Now, what you have to do? What you have to do? If the area of this subrectangle is delta Aij, so then what is going to be? I mean, what is going to be its this area is going to be given by what? So what we can do? We can simply consider. See, suppose I extend it here. I'm going to show you better picture in my slides later on. So then, this area is nothing but area of this whole region. I'm talking about this triangle, okay, polar triangle, minus area of this polar triangle. Is it okay?
Yes.
Fine. This equation is something like this. This equation is something like this. Okay. So this is length r I minus 1. This length is ri, right? And this angle and this angle, this part we may call it delta theta. This is nothing but theta j minus 1, right? So if I call this angle as delta theta, so this is simply going to be what? Or maybe I can call it delta theta j. So this is simply going to be half ri square delta theta j minus half ri minus 1 square delta theta j, isn't it? Because you know that area of a polar triangle is given by what? Half r square theta, isn't it? If theta is the central angle. So if you have a situation like this, right? So the area of this polar triangle is given by half r square theta, isn't it? This is the similar situation here. Fine. So then if I want to evaluate it, so this is going to give you your half your ri square ri minus 1 square. In the book, I mean, sometimes they simply use delta theta, only delta theta, and these they use simply delta ai. But I like to use delta aij because it corresponds to this particular point. Okay, so then this is going to be half your ri minus 1 plus ri theta j, fine. And we have already defined this. We have already defined this to be ri star. Okay, and let me call this one as delta ri, and this is delta theta. Is it okay? For the time being, it is fine, right? Okay. So now, what I am going to do? I am going to consider. This one. Say, suppose you have to integrate your f over this region, where D is the region given by this polar rectangle. Okay, so then what we will be interested in? We will be first interested in the product delta Aij, and then f of, and again now x becomes what? R
I star.
Yeah, so I'll change it to here. Yes, you are right. So ri star. So this is and theta j star. This theta j star, isn't it?
Yeah.
Fine. I'll be interested in this, and you know that one it is nothing but it is going to represent the volume of the column. Volume of the column. If of course, if I assume that your f of xy is greater than equal to 0, so it is going to represent the volume of the column that lies above this subrectangle and below the portion of the surface given by the function, I mean f of xy. Okay.
Right.
So now if I add all of them up as I goes from 1 to n, j goes from 1 to n, and if I take limit mn tends to infinity, mn tends to infinity, so this is what defines the double integral of the function f over the region D. And from this expression, you can see that eventually, I mean this one is what? This one is your Ri star delta Ri delta theta J, right? So that is why this one is eventually going to become your D f of r cos theta, r sin theta, then r dr d theta. This is going to be equal to this. Okay, so this is the way we are going to define double integral in a polar region. Okay, so let me just quickly go through the slides. So this is what I was talking about. You have regions like this, and you know how this region is defined. Here r goes from 0 to 1, theta goes from 0 to pi by 2. And again here r, the way the circles have been defined, this is a circle of radius 1, this is a circle of radius 2. So r is definitely going to lie between 1 and 2. And since we have considered only the upper half of those, angular region, so that is why theta goes from 0 to pi. Okay, so this is the formula for the transformation from Cartesian to polar, and then this is what we have done. Okay, so then this I have already explained, and this is what happens. And of course, I didn't break this one. They are calling it D. I am calling it. Sorry, they are calling it R. I was calling it D. Okay, and then what you do? Like I said, this one I still kept that as it is. I still didn't write anything about it. It is going to depend upon how you are going to perform the integration. So if you perform integration with respect to r first, then the limit is going to be a to b first, and after that, once you express it as a function of theta, then you integrate with respect to theta. And here one thing you have to remember, that this one, that beta minus alpha, it has to lie between 0 and 2 pi. Okay, fine. So let us work out certain examples. Let us work out certain examples. Say suppose you have to find the volume of a solid bounded by the plan j equal to 0 and the paraboloid j equal to 1 minus x square minus y square. Okay. Here. it is volume of the region that lies below this paraboloid and above the plane z equal to 0. Okay, so now you know that, I mean, just a minute. Is it going to be the paraboloid? I think this is going to be this, right? Or is it going to be paraboloid or it is square root? No, this is going to be paraboloid.
Without square root.
This fine. Yes, because paraboloid is okay, fine. Good. So now you know that, I mean, the paraboloid z equal to x squared plus y squared. So this is simply this, fine. Okay. So now if I want to draw z equal to minus x squared minus y squared, it is simply going to be this one. Okay, and then 1 minus x squared minus y squared. So that is simply what we have to do. We have to lift the paraboloid that we obtained from this one by 1 unit up.
1 step.
1 unit up. So if I lift it 1 unit up, so then it is going to look like, say, if this is 1, so it is going to be something like this. It is going to be something like this. Is it okay? Fine. This is x, y, this is z. Okay. So now you see that what we have to do, we have to find out the volume below this parabola and above this plane. I mean z equal to 0. Okay. So now, so this is, I mean, z equal to 1 minus x squared minus y squared. So basically what we have to do, we have to evaluate 1 minus x squared minus y squared dA, right? So now you have to find out this region D. Now you see that region D is nothing but this shaded portion.
Circle, a disc.
Yeah, it is a disc, right? And this disc is nothing but what? When z equal to 0. So when z equal to 0, it is x squared y squared
Less than
equal
equal to 1. Less than equal to.
Yeah, this less than equal to 1, because exactly equal to 1 will represent simply the perimeter. Okay, fine. So now, so that means this is going to be equal to 1, and that means your d in terms of r theta, it is simply r going from 0 to 1 and theta going from 0 to 2 pi, right? So this one, now if I convert it into polar coordinates, so then this is obviously, it is going to be 1 minus r squared, dA is r dr d theta, and this is r going from, no, firstly it is going to be theta going from 0 to 2 pi and r going from 1 to 2. So you may be asking why I'm so fussy about whether to write
R going from 1 to 2?
Pardon?
R going from 1 to 2?
0 to 1, sorry.
Yeah.
0 to 2. Yeah. So why I'm so fussy about it? Because say dr is first, so that is why I'm doing it. And I think in yesterday's class I forgot to tell you about one theorem, or maybe I had shown it to you. But let me tell you that if I have something like this. If I have something like this, say A to B, C to D, I mean fxy, dx dy, say something like this. Something like this. Say suppose x goes from A to B and y goes from C to D. So if this happens, and if your function, your f of xy is such that it is expressible as a product of a function of x only and y only, so then this integral, this is simply become your what? A to B
F1x
yes, and
dx
C to B F to Y T Y. Okay, so it is kind of variable separated. So now here you can see that it is exactly like that. So that is why this one I'll be able to write it as 0 to 2 pi 1 d theta and 0 to 1 0 to 1. So this is r minus r cube dr and simply integrate it and whatever you get. It is going to be the result. So this is eventually 2 pi and then half minus 1 by 4, right? Yeah, 2 pi into half eventually. Is it going to be pi? I think it is going to be pi. So this is going to give you what? 4 minus, no.
1 by 4.
1 by 4, right? So 1 by 4, so pi by 2 eventually.
Yeah.
Right? 2 minus 1.
Pi by 2.
It is going to be pi by 2. That's it. Okay. So let me try to work out another example. Okay. Before that, I'll just tell you one more. And again, see, whatever we did in Cartesian coordinate system, for polar coordinate system also, we can have type 1 and type 2 regions. Okay. So I'll just show it to you. So this was our example. Yeah, the answer is pi by 2. So now, say, suppose you have a region like this. You have a region like this. You have a region like this. Okay. So here you can see that what is happening here. That this R here the region is such that it lies between two curves given by r equal to h1 theta and r equal to h2 theta, and it lies between theta equal to alpha and theta equal to beta. Okay. Similarly, in this particular figure, you can see that. I mean, it lies between r going from A to B, and again two curves given by theta equal to g1r and theta equal to g2r. So in those cases, as in type 1 and type 2 region, what you can do, if f is continuous on a polar region of this form, So maybe I can call it as type 1 for polar coordinates. Okay. So then this integral, it becomes this. So what you do, firstly you integrate with respect to r, right? Because these two, curves, the two curves, they are curves for r given in terms of theta. So it becomes something like this. And similarly, what you can do, if you have the other way around, where theta has been expressed in terms of functions of theta, functions of r. So then you can use this formula. Okay. So now let us try one example with this. So this is the case. Find the volume of the solid that lies under the paraboloid. J equal to x square plus y square above the xy plane, and inside this cylinder x square plus y square equal to 2x. Okay. So this is kind of a complicated reason to draw, but I'll try. So under the paraboloid, j equal to x square plus y square above xy plane, and inside the cylinder x square plus y square equal to 2x. X square plus y square equal to 2x. Okay. So find the volume of the region which is under the paraboloid. given by z equal to x squared plus y squared above xy plane, and inside this cylinder, this given by this. So it is, my drawing may not be good, so hopefully you are going to excuse me for this. So obviously this is going to be my paraboloid. So now let us find this cylinder. So if you look at this cylinder, it is nothing but your x minus 1 whole square plus y square equal to 1. Is it okay?
Yes.
Right? So now let us see. Say, suppose. So this is centered at
1,0.
1,0, centered at here, and then radius 1. So it's going to be something like this, right? It is going to be something like this. Okay? So now what we have to do, simply if you extend it. So basically what we have to do, like I will have region like this. So this region, I have to find out volume of this region. Is it okay? Volume of this region. Okay. Now you can definitely see that if I want to find out the domain, so basically what I have to do, I have to integrate this. Above this region. Is it okay? Fine.
Yeah.
So this is okay. So and this is z equal to x squared plus y squared. So this is 0. So now let me concentrate on this because this is my domain. That less than equal to 1 is going to be my domain D. So here, if I plug in x equal to r cos theta and y equal to r sin theta, then you will see that this is going to give me r squared cos squared theta minus 2r cos theta plus 1 plus r squared sin squared theta. So this is equal to 1. So this 1 goes. This one and this one is going to give you r squared. So r squared minus 2r cos theta equal to 0. So from here, I am going to get r equal to 0 and 2 cos theta, right? 2 cos theta. Okay. So now, and again, see, basically, just a minute. Basically, this is my domain. Fine. Basically, this is my domain. Okay. So I have already found what the upper limit and lower limit for your r, which is in terms of if I want to find out, say d equal to r theta, I have already found out that r lies between 0 and 2 cos theta, right? So that means I must have the limit of theta. I mean, it is fixed. Limit of theta, it is fixed. So now, if you look at this, so obviously, I mean, in this quadrant, your theta goes from 0 to 2, pi by 2. Is it okay?
Yeah.
And in this quadrant, it goes from what? Minus pi by 2
Minus pi by 2 to 0. Yeah.
So theta is going to lie between minus pi by 2 to pi by 2. Is it okay? So
Yes.
then what is going to happen? What is going to happen if I want to evaluate this integral? dA. So this is simply going to be your x squared plus y squared. If you express it in polar coordinates, this is going to be simply
R square.
r squared, and dA is r dr
D theta.
d theta. And then your r goes from 0 to
2 cos theta.
cos theta, and theta goes from minus
Minus
pi by
pi by
2
2 to pi by 2.
pi by 2. Okay. So now what you have to do, you have to first perform integration with respect to r. So this is this is going to give you minus pi by 2 to pi by 2, and this is r cubes, right? So r to the power 4 by 4, 0 2 cos theta and d theta. So minus pi by 2 pi by 2. Anyway, for 0 I am going to get 0. This is going to give you what? 16 cos to the power 4 theta, right? Yeah, so this is 4 cos to the power 4 theta d theta. And then you simply integrate it. How do? You just simply convert it into 1 plus well, cos 2 theta by 2 whole square, isn't it? This one. Fine?
Yes.
Then from here, you are going to have a cos square 2 theta term. Again, convert cos square 2 theta into cos 4 theta. And finally, you will be able to integrate it. So the answer is, 3 pi by 2. No? Answer is 3 pi by 2. Eventually, you should get 3 pi by 2. Okay, fine. And again, here also you can see that it eventually boils down to, finding out the domain D, correctly. So that is what it is. So I'm just going to show you these slides, which I'm going to have a better picture. So this is how it looks like. This is how it looks like. I think my figure was not that bad. Okay, so this is about it. And after that, what I'll do, I'm going to tell you about the application of this double integral. So all those applications, in fact, you have already studied it in your intermediate physics or again in mathematics probably. But definitely in physics you have already studied. So I'm just going to quickly gloss through it, and you can study that on your own. Okay. So this is going to be about application of double integrals. So here formula for computing mass and then moments and center of mass. I'm just giving you the formulas here. This you please read it on your own, study on your own, and then center of mass formula. Okay, and then I have given also a couple of examples which you can work it out by using those formulas given in those slides. Okay, so what I'm going to do, I'm just going to, stop it for, double integral here. So that's what I'm going to start. I'm going to start your surface area. I'm going to start surface area. Okay.
Sir, I have a question.
Yeah.
What if the domain is like both type 1 and type 2 are combined?
Again, then you see which one is going to give you the easier way. You look at the integrand. Okay. You please look at the integrand, the function. Okay. So then, I mean, if it can be expressed both the domain, if it can be expressed both in terms of type 1 and type 2, then not only for polar coordinates, even for Cartesian coordinates also, you just simply look at the integral. I mean, which way it is going to be easier to work out. Then you go for the easier one. I mean, if type 1 gives you the easier part, then you go for that. And if type 2, you go for that. And again, similarly, what we did in Cartesian coordinates, that union concept. I mean, if it is neither type 1 or not type 2, but you can definitely express, and again, remember, whatever arbitrary reason you are given, eventually, you would be able to express it as a union of, type 1 and type 2 results. Okay, fine?
So all the
So,
regions can be expressed as unions of type 1 and
yes,
type 2.
yes, 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 definitely, definitely. I mean,
Oh,
like say the number of sub-regions, it may increase. Number
yeah.
of sub-regions may increase, but eventually you will be able to express. Definitely. Eventually
Okay.
you will be able to express. Okay.
Hmm. Hmm.
You have to, successively go on increasing the number of sub-regions if you don't find a type 1 or type 2 region out of that. Just okay. So the next concept is, like, this is a familiar concept. We already know it. Surface area. Okay. So obviously you have already heard that term. Surface area. What we did, we already did surface area for surface of revolution about an axis, isn't it? Fine. So we have some ideas about how to deal with that. But now, what we are going to do, we will be interested in surface areas. Of the graph of a function of two variables. And for simplicity, we are going to assume that the function that we are going to consider, it is going to lie above xy plane. But it doesn't necessarily mean that you cannot do it for any arbitrarily shaped surface. Okay. So then what you will have to do, as before, you have to divide the region or the domain of definition of the function. You have to divide it in such a way that you can work out something like this. You can work out something like this, or less than equal to 0. Accordingly, you can do it. So I'm just going to provide you with the underlying ideas, which is going to eventually lead you to the formula. Okay. So here, what we will be interested in, firstly, what I'm going to do, I'm going to talk about surface area of the graph of a function where the domain of definition is a rectangle. Domain of definition is a rectangle. So basically, it is something like the domain is given by r equal to. Okay. So once we know how to work it out over a domain which is a rectangle, then you know that any general reason we can easily extend that idea to, right? We have already seen in multiple integral. Okay. So now what I'm going to do, say, suppose I'm going to consider a suppose I am considering this rectangular region. This rectangular region. Okay. And this is AB and this is CD. Okay. And I am considering the graph of a function, which is say something like this, So this is j equal to f of xy, and as before, as I have told you, for simplicity, we are assuming that f of xy is greater than equal to 0. So that means the surface lies above xy. Okay. So then what I am going to do, again, I am going to what, subdivide this rectangle into sub-rectangles. This rectangle into sub-rectangles, like this. Okay, fine. So now, say suppose this is the I mean sub-rectangle created by the sub-intervals this. Okay, you know the underlying concept. So what we have done, we have divided AB into n sub-intervals like this, okay, and CD into m sub-intervals like this. Is it okay? Fine. So now, if you consider the graph of the function for this subrectangle, and what we have done, say suppose we are considering this point is nothing but just a minute, we are calling it x I minus 1, so just a minute. So this is going to be, yeah, and yeah, suppose this is xi minus 1, this is xi, then yj minus. Okay, suppose I am considering this point xi yj. Okay, fine. So then what I am doing in this subrectangle, I am considering the surface that is being generated over this subrectangle Rij. Okay, so this is my subrectangle Rij. Okay, so and this surface area, let me call it as delta Sij. For the time being, it is fine, right? So now, I mean, if I consider a tangent plane, to the point xi comma yj, so then what it is going to do? Then what I am going to get a tangent plane like this. Is it okay? I'm going to get a tangent plane like this at this point to that surface. So now what I'm going to do, I'm going to consider the tangent plane that simply lies above this rectangle. So it is going to give me some plane like this, and this plane I'm going to call delta t ij. Okay. So now, if the area of the tangent plane is delta Aij, and of course we are going to assume that this length is say delta x, and say this length, suppose this is delta y. So delta xi, sorry, and this is delta yj. So then what is going to happen? So then just a minute. Yeah. So Now, if we are able to find out, the area of all those tangent planes lying above some rectangles like Rij, and if we sum them up, and if we let m and n tending to infinity, so then that is going to eventually give me the area of the whole surface. Right? Yeah. So that is the concept that we are going to use. So now it is going to boil down to finding out your yeah, the area of this small tangent plan given by delta Tij. Okay, let me see how the situation is. Let me consider a magnified version of that. So what I'm going to do, see. Okay. Okay. So okay, fine. This should be good enough. So the tangent plan, it is going to be something like this. Tangent plan, it is going to be something like this. Okay. Yeah. Is it fine? Okay, the tangent plan is going to be something like this. So this plan is nothing but delta Tij. Okay, and let this be vector A and this be vector B. Okay, fine. So then you know that the area of this plan, it is nothing but the area of the parallelepiped created by, not parallelepiped, sorry, parallelogram created by the sides A and B. So it is simply going to be given by this. Is it okay?
Yeah.
Fine. So now let us see this situation here. So now you can see that I mean this plan or for that matter this vector it is going to lie in the xz plan. Okay.
Yes.
Fine. Because it is cut out from a plan from a plan which is nothing but this plan, isn't it, corresponding to where your y is constant. Similarly, this vector b, it is going to lie on yz plan. Is it okay? Fine.
Yes.
So now let me see this scenario. In xj and yz plan. So once I do it for xj plan, it will be clear for you what is going to happen in yz plan. So this scenario is going to be something like this. Say this is x, this is j. Say this is delta x. Suppose this is my vector A. So then see, just a minute. In fact, the way I am drawing it, let me consider this point. Let me consider this point because it will be easier for you to visualize this. So then A and B will start from here and here. So basically x I minus 1, y j minus 1. So then it is going to be easier for me because if this is x I minus 1, then this is going to be x I. It is going to be easier to visualize. Is it okay? Fine. So then what is going to happen? What is going to happen if I, and again I suppose I am considering my tangent plane at this point, x I minus 1, y j minus 1. So now if you look at this vector A, so then if this is delta j, okay, so then if this angle is say theta, this angle is theta, so then you know that your delta z by delta x, this is equal to tan theta, isn't it?
Yes.
Fine. And again, remember, this is nothing but A vector is nothing but a tangent to the curve, which has been obtained by intersecting it with a plane, given by what? Given by y equal to y j minus 1. Is it okay? Fine?
Yes.
Fine?
Yes.
But fine. So it is something like this scenario is something like this. Okay. And then you know that from the geometric interpretation of partial derivative. So this is simply the derivative of fx at this, isn't it?
Yeah.
This is nothing but the slope of the tangent, right? So that means your delta z equal to fx at x I minus 1 y j minus 1 delta x, right? So in Stewart book, they use the point xi comma yj. Eventually, as you let mn tends to infinity, it is going to be the same. But I think in order to explain the concept, if I use xi minus 1 yj minus 1, because that is the point nearest to the origin, I mean the analysis will look much better. Okay, there shouldn't be any confusion. Whatever you read in Stewart book, but the analysis will remain same. Okay, so now, so that means what is happening out here? So then, if you look at the vector A is simply delta xi plus delta j k, right? So this is equal to delta xi plus fx at xi minus 1 yj minus 1 delta x k. Fine? Is it okay?
Yes. Yes.
Similarly, your B is going to be delta yj plus fy at xi minus 1 yj minus 1 delta y k. Fine? So that means if I want to find out A cross B, then this is going to be I j k delta x 0. Let me simply call it fx delta x. I'm not writing at what point. That is fine. At this point, you know. So then this is delta y, then fy delta y. So then this is equal to I. So it is going to be minus fx delta x. Of course, this is delta x I delta y j. Huh? So I'm simply writing it as delta x delta y. Don't worry about it. Okay. So delta x delta y, and then j. This is going to be minus. So again, so this is I. This is minus fy delta x delta y j, and then for k simply plus delta x delta y k. Okay, so this is simply going to give you minus fxi plus, sorry, minus fyj plus k delta x delta y, right? So that means if I want to find out the area of that subplane, so it is simply going to be square root 1 plus fx squared delta x delta y, right? Okay, so basically what is happening? So that means your delta aij, so that is what? That is simply what? 1 plus fx at xi minus 1 yj minus 1 whole square plus fy at xi minus 1 yj minus 1 whole square and delta xi delta yj. Is it okay? Fine.
Yes.
So now if I take this sum, if I take this sum, I goes from 1 to n, j goes from 1 to m, and again limit mn tending to infinity, and then of delta I aij. So this is simply 1 plus fx at xi minus 1 yj minus 1 plus fy whole square xi minus 1 yj minus 1, and then delta xi delta yj. So then you know that. And again, one important thing I missed, that the function f is such that the first order partial derivative fx fy, they are continuous. They not only exist but they are continuous. That I mean condition has to be there. So you know that this is simply nothing but it is over the integration of this over the rectangular region R, and then 1 plus fx squared plus fy squared, then dA. Isn't it? Because delta xi delta yj, that was nothing but that area of that subrectangle lying on xy plane. Is it okay?
Yes.
Fine. So this is the formula for surface area. This is the formula for surface area. So I'm going to show you this slide. This is what it is. See, I am considering a this I don't like. Again, let me tell you, this I don't like. According to me, this point should be xi minus 1, yj minus 1, so that you can define the rectangle better. You got my point now? What I want to say, although it is, see, if you consider this rectangle to be, I minus 1 comma xi cross yj minus 1 comma yj. So according to me, this point should be xi minus 1 yj minus 1. Okay, fine. So this is what is happening. This is what is happening. So I have already explained to you all the underlying facts. So then you know that area of this surface S, it is simply nothing but the sum of all the areas of those small tangent lines. Consider that its point like this, and eventually that is going to lead you to the area of the surface with equation z equal to this. And again, as I have told you, fx and fy, they have to be continuous. It is simply given by this. And again, dA, I mean this according to your convenience, you just adjust it. And again, you should remember, see, the formula is straightforward, but how one has reached that formula, that is important for us also. Okay. So now, if what you have to do, you have to simply integrate this function over this domain D. So again, everything is going to boil down to finding out that domain. Okay. So let me just do, I mean, one example, one problem, and after that, I'm going to finish. So this is one example. Find the surface area of the part of the surface this that lies above the triangular region T in x vector with vertices this. So again, I am going to just find the area for you, and not area, sorry, the region D, and am I still audible?
Yes. Yes.
Okay. So here z equal to x squared plus 2y. Okay. So zx equal to 2x, zy equal to 2. So 1 plus zx squared plus zy squared. So this is going to be equal to 5 plus 4x squared, right? Okay, so basically we have to integrate it. So now let me concentrate on the region 0, 0, 1, 0, 1, 1. Sorry. So 0, 0, 0, 0, 0, 1, 1, 0, right? 1, 1. Let me just check it again. Yeah, 0, 0, 1, 0, sorry. So this is 0, 0, 1, 0, 1. Okay, fine. So this is my domain. Okay, fine. So then your surface area, or sorry, area of the surface. So this is simply your D, then this one, 1 plus Am I back now?
Yes, now you are back.
Okay, okay. So this we have already found out, 5 plus 4x squared. So now let us concentrate on this. And again, see, this region is such that you can consider it as both type 1 and type 2 region. Okay, so if I consider it as a type 1 region, so obviously I am going to have my x going from 0 to 1 and y from bottom to top, and this line is definitely y equal to x, isn't it?
Yes.
Right? So
Yeah.
y equal to 0 to y equal to
Yes.
x. So it is going to be dy dx. So you will see that once you integrate it with respect to y partially, you are simply going to get what? Y is going to come, and y is 0 to x. So there is going to be 1x, and it is beautifully formed because the derivative of this is going to be simply 8x. So eventually you can easily do this, right? So I think I will stop it here. In my next class, I'm going to do one more example, and then I'm going to move to trigonometry. Okay, thank you.